Alright, dear students, hello. Another lecture on numerical approximation of DAEs. Today it's the second part. I don't count the zero part, which was introduction to numerical approximation of ODEs. Well, last week we had how to apply an RKM to a DAE, and we also found that RKM are invariant under equivalence transformations, so that we found last week. And then I will argue again that we can consider this very special DAE for the analysis, how to apply an RKM for two LTI, linear time invariant DAEs. Okay, and today, so this was last week, and today we will look into consistency error, convergence. There will be some stability involved, and then there will be a little note on RKM for linear time varying DAEs. That's all we will have today. All right. Well, so maybe we just start. We were looking at DAEs of this type: Ex dot as Ax plus f of t. X of t0 is x0, and we were assuming that EA is a regular matrix pair. So we were arguing that this should be regular because we want to approximate the solution, and if there's no solution, then there's no sense in approximating it, and if there are infinitely many, then we cannot expect something useless out of a numerical approximation, because it's not clear which solution is approximated. So this a regular matrix pair is like very fundamental and basic. And then we did all these derivations, finding that RKM this like interchanges nicely with considering PEQ x tilde dot as PAQ x tilde plus PF of t. So we can assume that P and A is in canonical form. Then also we had that these we found that the parts really decouple as well. And so we can assume again for the analysis, because that's just theory, and in practice we cannot bring these equations into canonical form. We can assume that the E matrix is actually this matrix, 0, so a lot of zeros on the diagonal, and this nilpotent matrix. So E is this matrix and R nu times nu, and here's this nu, and this is directly the index of this matrix. We can assume that A is the identity, just as a reminder, what is the identity in R to the nu times nu. And then we will assume that x of t is given as x1 to the x nu of t. I hope if we have a t with the x, then this subscript it's clear that it's a component of the solution. What else do we have? Well, f of t then as well as a function with with new components. So there's f1 of t and up to f nu of t. All right, so we can assume that the DAE is given in this particular form. Okay, and then there is the theorem for that. Theorem 5.2. That's also the number that it has in the script. And it says, okay. Well, let's call this matrix just for later reference. We call this E the NU matrix, meaning the nilpotent matrix in standard form of size nu, or of index nu. Now the theorem namely says the local error namely x of ti plus 1 minus xi plus 1, and this xi plus 1 computed on the base of the exact x of ti. This is the local error. Like we had this consistency error. If you maybe recall the consistency error for ODEs, this was defined as minus, here's this function vti hi and x of ti. Okay, so this is like applying the function but with the correct data. This gives us the consistency error as we had, and so I just want to put this here in this form. So the local error of an RKM applied to the special DNV x dot as x plus f reads, so behaves like this is okay, reads and behaves like, to somehow save this. So this was this. We have some explanation to that. And now we continue the sentence, behaves like x of ti plus 1 minus xi plus 1 is this Landau symbols again, this big O notation. Here's the step size, and then we have this parameter kappa minus nu plus 2 plus O another kappa nu minus 1 minus nu plus 1. This goes all the way down to O of h. Get the exact notation. Yeah. H kappa 1 plus 1. So if you think of an ODE, there we had the local consistency error to be, so ODE, there we had EH as O of H P plus 1. I think that's how we defined it. And well, you see similar things here with this kappa, but you also see the index here, this new. So this somehow relates to the index as well. And this kappa j we have to define where kappa j and j ranges from 1 to the new. So that's kappa 1, kappa new minus 1, kappa 1, or the other way around, kappa 1, kappa 2, up to kappa new. Is the maximum number such that we have two conditions. This A condition was beta transpose this A matrix. So this RKM was beta transpose and this RKM is A beta gamma. And here you see the coefficients again, a to the minus k times a vector of only ones. That's one vector. As this is now the condition, is beta t l to the minus j gamma to the j minus k divided by j minus k factorial, and here k should range from 1 to j minus 1. Yes, j minus 1. And for k's that are larger than the j minus 1, there's another condition, and this condition reads beta a to the minus j gamma in the kth power should be the same as k factorial O divided by k minus j plus 1 factorial. And this goes for k j plus 1. And there, well, and there should, well, the maximum number here is then the kappa j. But it could also be infinity. We will see that there is a case where this is infinity. Okay, such that kappa j is the maximum number, such that here that this holds for all k. All right, that's the theorem, and the proof of that. I would just provide the idea here. Oh no, basically not really the idea, but just the first steps, because you can have a look in the script. There you see the proof. In the end, it's a bit technical, but I think the first steps are interesting, and they are not laid out too well in the script, and I just want to explain them how one gets these first formulas, and then from the formulas how to get to these relations. I think that's more straightforward, and so to provide a bit more idea how this proof works, I will just lay out the few steps. So we know, here, for example, last lecture, the solution is given as, and here the solution is this xi, so all the stage values. So that's needed to define the Runge-Kutta update, and so one needs to compute the stage values. And in this case, it is given by, I think I can take in color, by I as chronic n minus h a times di. the I knew. So this was the SDA matrix, but in our case, since we just consider this particular, here the A is the I knew. So we have to solve the system this for the stage values, and the right hand side is the ZI, and in this case it was given as XI plus, do I have it? FTI plus gamma 1H all the way down to F of Ti plus gamma S times H. Okay, so we know the solution. Okay, since we consider the consistency error, what we will do actually is putting in here the exact solution, X of Ti. This will be then the consistency error. Typically one only has the numerical approximation, but to consider the consistency error, so we compute on the base of the exact approximate. At some point we will put in the exact solution here. Okay, and then by this we get the stage values, and then you know how the Runge-Kutta methods work. If you have the stage derivatives, then you know the new iterant. So the question is, this will give us a representation of the stage derivatives, and with that representation of the numerical solution. Okay, and that will be used to do the estimates. Okay, and then we had this perfect shuffle matrix pi, which could switch these terms. So we apply this here, then we have P, then we have P transposed IS Kronecker N minus HA Kronecker I new. Here we also include this, so this is the identity, we can include this here, xi that, and well, this was multiplying with the pi t. This will give us the pi t pi transpose zi. And well, this means that this shuffles here. So here we will have this n times is minus ha minus I new times HA matrix pi t x I dot s pi t z I. And this, well, now we invert this here, and then also we invert this, which is multiplying by again. So from here we get that xi vector is basically, well, we have the pi, then this matrix inverted and applied to here, ptzi. So this gives us the complete stage values with that. Okay. Yeah. Yes, yeah. Okay, then we maybe need some regression that this matrix here is basically, so we had this last week. This is okay. This is minus HA on the diagonal, and the n block. No. And this IS blocks on the first upper diagonal. Okay, so this is the so all this together is exactly this matrix. We haven't inverted this yet, but it's straight for or one can show by if you notice perturbation lemma by von Neumann, for example, that the inverse to this matrix is HA to the -1. Here we will have HA. We'll have HA to the -2, and this goes to HA to the -S. And here we have HA to the -1 on the diagonal. HA to the -1. Okay. Here also HA to the -2. This is the inverse of this matrix. Meaning we have that the xi, this state value is still this shuffle matrix. Here the inverse, can write them a bit nicer. I to the -1, h alpha to the -1, h alpha to the -2, h alpha to the -2, and here we have h alpha to the -s. Okay, this is this, and PTZI, PTZI. Okay, so this is this, and now we have to think about what is PTZI. PTI, this P transpose was shuffling the Kronecker product such that it in fact changes the row of the order of multiplication. And well, let's see, what does this mean here? So this should be another color, another regression. So we have PTZI is basically, why do we have the ZI here? X of Ti plus F of Ti plus gamma 1h, X of Ti plus F of Ti plus gamma sh. This is the same as PT, and now I put this in quotation marks because that's like a misuse of notation, but with the right formal definition you will see that this is okay. So we will write this as the vector, okay, as a Kronecker product, namely, so this will be gamma 1 up to gamma s, Kronecker X of Ti plus F of Ti plus, okay, and that's, so to say, now here's where this product will take part on TIH. So this is really just about how this vector is ordered, but with the help of such a Kronecker, or with misusing such a Kronecker, one can rewrite this. Well, and let's just check this for one. So here this strange rewrite is, so the first part would be basically gamma 1 times F of ti plus here the gamma 1 should go h in this notation. And well, let's write this. Oh, I forgot the xi. X of ti, well, that's the same. So here's where this gamma 1 should go. If we might define this as a kind of multiplication, and then this will be x of ti plus f of ti plus gamma 1 h. This would be the first entry of this Kronecker product vector, and that's this here. So like formally one can assume that this, oh, maybe to say it right, this vector is ordered as if this was a Kronecker product. And then since the pi t changes the ordering such that it's a Kronecker product but the other way around. So this will be now applying this Kronecker, this permutation. Put this again in these marks. Then we will have x of ti plus f of ti plus h, and this multiplication should take part here. This like Kronecker thing. Gamma 1 to the gamma s. Again in quotation marks. Okay, and then this will be all the time, this will be, so xti, fti is a vector as well, so this will be huge vector. This will be x1 of ti plus f1 of ti plus multiplication happening here h times this gamma vector, gamma 1 to gamma s, and here we will have x nu ti plus f nu ti plus multiplication happening here. This somewhat ill-defined multiplication, but yeah, just a matter of notation. Gamma s. Okay. So this will be yeah, I just write down the first part. This will be x1 ti plus f of ti plus gamma 1 h, x1 of ti plus f of ti plus gamma 2h, so on. Then here will be x2 of ti coming up, and in the end there will be x nu of ti plus f nu ti. So this will be, this is this resorted vector, and we call this part here, this will be zi1, this part here will be zi2, and the last part will be zi nu. Okay, and this is how this product how this permutation changes this vector accordingly. And why is this interesting for us? Because with that we get xi that is still, we have this permutation here, this funny matrix, and now here we have these other, here we have zi1, zi2, I new. With ZIL being defined as XL of Ti plus FL of Ti plus comma 1 H and XL of Ti plus FL of Ti plus gamma SH. Okay, so this is what this shuffling permutation does to this vector. Okay, still we are not right there. Okay, but almost. Now the RKM says that like the new xi plus 1 is given as x, in this case x of ti, because we think that we start with the actual value, plus h some j is 1 to us, beta j x I j, the stage values, and in fact they are all to be found here. So this is xi1 dot up to xis dot. Okay, and now we do another rewrite of this product here. So we will have xi plus 1 as x of ti plus h. Let me just write this down and then we will see that this is okay. This will be beta 1 times is, then another entry of this vector will be beta 2 times is, and so on, beta s times is, and this will be multiplied with this vector xi1 dot up to xis. Okay, do you see this? Well, multiplication goes like row times column, and what happens is that this will be exactly the sum here. There's nothing changed from here to here. It's just writing a sum. Maybe it's easier to see for vectors as an example. So if we have like the sum ui vi, I is 1 to n, this can be written as u1 to un times this vector v1 times vn. And now this here is all scalars, and so this can be also done for vectors, and this here is a little matrix all the time multiplied by a vector, and then you get a vector again. But this is interesting because this can be written as a Kronecker product as well. This is h times beta transposed Kronecker is. Okay, and now we put in here what we know as it. So this is is times, give me another color for that, so we replace this part here by what we know here. So, okay. Yes, maybe I take another page for that. So this will be xi plus 1 is x of ti plus h times beta transposed Kronecker is. This is this part here. now we replace this vector by this representation of that. So this is times pi t, this matrix, this notorious matrix. H alpha to the -1. And here we have this. How did I write this here? Z1, Zi1 up to Zis. Okay, and last time using this permutation, this will now turn those twos, because since here's a vector on that, and well, permutating a vector from the left, this will always be just the one. So you may miss the pi here on this side in order to do this shuffling, but well, in fact, here the pi is just the one, because from this side there's not much to shuffle if there's just the vector. Okay, and so this will shuffle again. So we will have xti as xti plus h times is Kronecker beta transposed times this matrix times this vector, and this is x of ti plus h. What does this look like? Actually it looks like this. So beta transpose, this is a long vector, beta transpose, this is a long vector, beta transpose, a long vector, up to beta transpose, this long vector, times this matrix. Okay, and then the important point here, just the first component of xi plus 1. This is what is needed in the proof later, and this will be, I just write this down and then you see this probably. This will be xi plus 1, the first component from here, that's easy. x1 of ti, just the first component of here, plus h, and the first component will be the first row of this matrix multiplied by what follows. So this will be the first component of the vector that's created here. So this will be beta transposed 0, 0, a lot of zeros. This matrix here, h alpha to the -1 and so on, times the zi1, zis. And you see that this basically picks only out the first rows of this matrix, because these zeros they meet here, and they this will be all gone in this final product, and that's then how one arrives at this xi ti plus h. Okay, then one can like the first row here, this will be, I just write down, so this will be beta transposed, and what's left here is this times this, so this is this product j equals 1 up to s, ha to the -j, zij. Okay, and that's how one gets to this expression of the first component of the numerical error. And then, well, what follows is see the script. Okay. With that, we are done with the proof. And then I will just add on with the theorem. So once we have consistency, and with that we have these conditions for consistency. Where are they? Here. These are the conditions for consistency for a Runge-Kutta method. And we come to theorem 5.3, which will then give us actually convergence of the problem. And this goes, consider RKM with a to the minus 1 exists, so an implicit, and a DAE, in this case general form EX dot is AX plus F of T, with a regular and index of this matrix pair is given as new, and let these kappa j goes from 1 to the new, be given as in theorem 5.2. Okay, now that's important. Furthermore, assume that we have this condition, and this is a condition that is only a condition on this Runge-Kutta method, that beta transposed A to the E, A with a vector of all ones. So we assume that this quantity here is less than 1. That's a stability condition. I will get back to that in a second. And this means that then the RKM is convergent of order minimum. It's not so easy like for one less than equal than j, so j ranges from 1 to new. Here is the p, that's the order that it has for ODEs, and here we have these consistency orders, kappa j minus new plus should be j, right? Okay, students, I made a little mistake here with recording, and so the second part I have to repeat once more and piece it together. Sorry for that. So we were at this theorem 3.2. What color are we in? So this was theorem 5.2, I mean. Oh no. Yeah. So we were in theorem 5.3, and we need these kappa j, the quantities as they were defined in theorem 5.2. And if we have them, then we need to assume this stability condition, which is a condition of the RKM only. So this is really, there are RKMs that have this condition, and there are others that don't have it. But if all this is fulfilled, then if we apply the RKM to the general DAE, then this is convergence of the order the minimum over j ranging up to this index or of the pair. and here's the order for the ODEs, and this is the error for that comes from the DAE part, and here you see this kappa j again. And the proof for that is in theorem 5.12. It's technical, but also gives you some insight what happens there. But it's technical most of the time. And instead of going through the proof, I would rather like to go a bit through what this rho means. So the rho was this condition of the RKM, the stability condition. And there are RKM methods for which this rho equals 0. And these are super stable method, or they are super stable. And what this means, let's have a look at the implicit Euler scheme for that. So this is a Runge-Kutta method. If we write this in the butcher tableau, the A matrix will be just the 1, the beta transpose will be just the 1. And then, well, if we compute this, 1 minus this beta matrix, just the 1, the A is just the 1. We pick this one vector, it's also just the 1, so this will be 1 minus 1 times 1 minus 1. This will be 0. So for implicit Euler, obviously this rho is 0. And in fact, if we apply this to an index 1 problem, which is given at this, so 0 times x1 dot is x1 plus f1. So think about here x plus f. So this was the general problem, and if this is index 1, then this is just the 0 matrix of size 1. So this is what we get here, and the solution we know directly as x1 is f1 minus t, f1 of t. Now if we apply the implicit Euler method, so we would have e minus ha x1 plus 1 is exi plus f h times f of ti plus 1. So this would be that. And here we have the 0 minus h, a is just the 1, xi plus 1, 0 times the xi, and here the right hand side at the new point of time, we divide by or multiply with 1 over h, and then maybe with minus 1 over h, and then we get xi plus 1 as f of ti plus 1. Comparing this to that, well, we just see that this is an exact integration. Meaning the stiffly accurate schemes, if they are applied to these super stable schemes with rho is equal to 0, and we will show this later why this is the case. If they are applied to index 1 problems, then no, they don't have a consistency error, which is nice. And okay, maybe at this point of time, typically we have EA to be in this Jordan form. It will be like this. So this will be index 1. And here we have to change here the identity. And this of course only means that this part here is exactly integrated. But this part still is an ODE which has to be integrated. But this is right in line with this estimate, because the convergence order is the minimum of what we get for the ODE part in this case, and the DAE part. And well, if this is infinity, then the approximation order is just defined by this by the ODE part. All right, now some more general thoughts on these stiffly accurate schemes, and they come with this condition that the alpha Sj, so the last line, the last row of this matrix A, equals the beta. And I have tried to put this here in this butcher tableau. Here we have the beta transpose typically, and now this part here of the A matrix is also the beta transposed. Then one knows that consistent schemes, for those we have beta j is equal to 1. So the sum over all beta j is equal to 1. You can have a look at the theorem by Butcher. Well, that's like the easiest condition to check that this should be the case. but I have tried to motivate this here with this example. If one looks at this easy ODE, x dot is just a constant, then this is what the x looks like. And in particular, one has x ti plus 1. So this one is just the x of ti, this one time plus h times the constant, because the constant is basically the slope. Okay, and then this also means that if we compute the stage values, because this is just the f of ti plus gamma jh, this will be always the c. This will be constant. So the Runge-Kutta approximation will be xi plus 1 is xi plus h, the beta j, the stage derivatives. They will be all constant. So we will have xi plus 1 is xi plus h times this constant. We can put this out of the sum. And here's the sum over the beta I, and then it makes a lot of sense to have this 1. Otherwise, we weren't able to even integrate this very easy function. And then the other condition that one often has, and in fact all schemes that you will encounter, they have this condition that the sum of the beta of the alpha JL, so taking the sum of such a row, the sum over that this should be the gamma j. Yeah, and that's what's said here, the alpha JL, if we sum this row, then we should get the gamma j of that. And this relates to, well, here that's how these gamma j's, the stage values xij are defined. They are defined through this alpha jl via this, and well, you see some similarity here with the beta j, but only here this is the xi plus 1 approximates this, and the xij can be seen as an approximate to xi of gamma j plus ti plus gamma jh, and so it also makes sense to have this to be summing up to the gamma j. This is not true for all schemes. There are schemes that don't have that, but most all relevant schemes have it. All right, and then if we then know that the sum is the gamma j, we know that the sum of the beta j is the 1, and from that we can conclude that the gamma s is the 1, because like these all sum up to gamma s, and these are all the beta, and the beta sum up to 1, so the gamma s will be 1. And then from the condition that beta is the last row of the A matrix, we can write the beta as being this vector that picks out the last row of the A matrix. We can have a look at this condition here, beta transpose alpha to the minus 1 gamma k. I will tell you in a second why I consider this. This is given us that. This here cancels out to be the identity, so we are left with this here. This is the last component of the gamma, it's the gamma s to the k, and for these schemes that we consider here, this will be just the 1. And whatever the k is. So 1 to the k is always the 1. And now why we were considering this strange condition, we look at the condition, we look at this condition here. This were the consistency condition for the Runge-Kutta methods. And here this B condition wrote that B transpose alpha to the minus j gamma to the k should be equal to our right hand side. If we look at the case j is equal to 1, then we will have beta transpose alpha to the minus 1 gamma k. What we just calculated will be 1, and k factorial k minus j plus 1 factorial is k factorial, so we will have a 1 here. And this means that this kappa 1 is infinity for stiffly accurate schemes. And this means RKM applied, stiffly but these were this with the special condition that that is kappa 1 is infinity, stiffly accurate RKM applied to index 1 problems preserve the order for ODEs. Okay, and that's very good news. This means that if you have a stiffly accurate scheme and you apply it to an index 1 problem, then there's no big difference to an ODE. All right, actually I wanted to talk about time varying DAEs too, but since time is already over more or less, we will just talk about this together on Friday. See you.